Alright, this is the second video about simplifying rational expressions. We'll look at multiplying rational numbers, meaning fractions, and then extend that understanding to rational expressions, and then do the same for division. So the first example we want to see here is an example of integer multiplication. We can think of this multiplication 4 times 3 as 4 groups of 3, and we can draw that as 4 groups of 3. To see that we get 12 as our answer. Now I'm guessing that you all knew that, but it's important to start with the basics so that we can build a common language. Looking at 2/3 times 3/4, the way we can think of that in the groups of language is 2/3 of 3/4. So what I'm going to start doing here is drawing a picture of 3/4. So I've divided my whole into 4 equal pieces, or at least they're supposed to be equal, and then I'll shade in 3 of those 4. So that's my picture of 3/4, and what I want to do here is take 2/3 of that. So I'm going to divide my whole into thirds going in the other direction, and if I just focus on the shaded part of my whole diagram from when I made 3/4, I want 2/3 of that. So this rectangle that I'm outlining here is 2 pieces out of 3 equal-sized pieces that were my 3/4 of the whole. So 2/3 of 3/4 is that area outlined in green, and that is 6 pieces out of 12 pieces total. So we can see that the numerators, which were 2 and 3, multiplied together to become 6 because my outlined area is a 2 by 3 rectangle, and my whole rectangle is now a 3 by 4, a 3 by 4, which gives us a denominator of 12 equal-sized pieces in the whole. So we can see generally that when we're multiplying fractions, we can multiply the numerators to get the new numerator, and we can multiply the denominators to get the new denominator. Alright, let's extend that to rational expressions. So here I have 2 rational expressions that are fully factored in both the numerator and denominator. So what I'm going to do is just apply that understanding from the fraction multiplication problem that we just did and multiply the numerators together. So I get x plus 3 times x minus 1 times x plus 4 times x plus 7. And my denominator is going to become x plus 4 times x plus 3 times x plus 7. So using the information that we learned in the last video about giant ones, I can see that this expression can be rewritten as x plus 3 over x plus 3 times x plus 4 over x plus 4 times x plus 7 over x plus 7 times x minus 1 over 1. I need that 1 to be in the denominator of my last term, because when I multiply all of those denominators back together, I should get x plus 4 times x plus 3 times x plus 7. So all of these terms, all these purple terms are giant ones, and we know that multiplying by a value of 1 doesn't change the value of the expression. And so our final simplified expression here is just x minus 1. Remember that we have some excluded values. So there are some values that make the original expression undefined that may or may not make the new expression undefined. So when we call two expressions equivalent, what we're saying is that for every x value that I plug in, I'm going to get the same output. Well, in the original expression, when I plug in certain values, I'll get an undefined output, because certain values will make the denominator equal 0. So to find the undefined values, I'm looking for the values of x that make the denominator of the original expression equal 0. So I'm going to write out that denominator here. I'm going to set it equal to 0, and now I see that I can use the zero product property. So the value of x that makes x plus 4 equal 0 is negative 4. The value of x that makes x plus 3 equals 0 is negative 3. and the value of x that makes x plus 7 equal 0 is negative 7. So my final answer, my final simplified expression is x minus 1, but we don't want to plug in negative 3, negative 4, or negative 7. Okay, and so this is my final answer. Let's see what this looks like when we graph it. So here I have the original expression as a dotted red line. I got a little cut off in Desmos there, but that's our original expression. And then our simplified expression is a solid green line. So we can see that the graphs of these two expressions overlap as far as we can tell, given that the window that we have here. So that's good. That justifies our work and makes me think that they are equivalent. Now look at this original expression. When we plug in x equals negative 3, we get out an undefined value. Same with negative 4 and negative 7. But when we look at the original expression, when we plug in negative 3, we don't get an undefined output. We get negative 4. When we plug in x equals negative 4, we get negative 5. When we plug in x equals negative 7, we get negative 8. So we're seeing this discrepancy where when we plug in negative 3, negative 4, and negative 7 to the original expression, we get an undefined output, but that doesn't happen with our simplified, supposedly equivalent expression. And so what we just have to do here is we say, well, for every x value, the original and the simplified expressions are equivalent, except for x equals negative 3, negative 4, and negative 7. Let's go on to a fraction division problem. So I'm going to show you a way to do fraction division that uses this idea of the giant 1, even though you may have seen other ways to represent fraction division in class. So when we look at 4/5 divided by 2/15, I'm going to first rewrite that so that it's a fraction. So I've got 4/5 divided by 2/15. Fraction and a fraction isn't usually what we want, but for right now it's going to be okay. What I want to do is multiply this by a giant 1 so that I'm not changing the value, but I am changing the way the fraction looks. And what I want to do is choose a giant 1 that gives me a denominator of 1 when I write out the simplified version. So I'm going to choose for my denominator to be the reciprocal of my original denominator, 15/2 instead of 2/15. And because this is a giant 1, I need the same thing in the numerator. So when I go through and multiply this, in the denominator I'm going to have 2/15 times 15/2, which gives me 30/30, which is 1. That was my goal. And in the numerator, I'm going to have 4/5 times 15/2. Now I can simplify this to be 4 times 15 is 60. And 5 times 2 is 10, so 60/10 is equivalent to 6. But what I really want to do is notice that this interesting pattern happened. We started with 4/5 divided by 2/15, and we ended up rewriting it as 4/5 times 15/2. So what we really want to take away from this example is that dividing by a rational expression is the same as multiplying by its reciprocal. A reciprocal means when you flip the numerator and the denominator. Alright, so when I look here, I've got a rational expression divided by another rational expression. Once again, they're all factored for us, so that's going to be convenient for right now. And the first step I want to take is to rewrite this expression so that it's a multiplication problem instead of a division problem. So my first term stays exactly the same, but I'm going to rewrite this as multiplication by the reciprocal. So my new numerator is x plus 4 times 2x plus 1, and my new denominator is x minus 3 times x plus 1. Alright, and now that I've got a fraction multiplication problem, I can write this as the numerators multiplied together. X plus 10 times x minus 3 times x plus 4 times 2x plus 1 divided by 2x plus 1. Oops, that's a little hard to read. 2x plus 1 times x plus 10 times x minus 3 times x plus 1. So instead of rewriting this as all of my giant ones multiplied together, I'm going to notice here that both numerator and denominator are written as factored, in factored form. And so I'm just going to look for some giant ones. I see that I can have an x plus 10 over x plus 10, which is the same as multiplying by 1. I see 2x plus 1 over 2x plus 1 is the same as multiplying by 1, and x minus 3 over x minus 3. And so my final simplified version is a numerator of x plus 4 and a denominator of x plus 1. I want to be careful that I note the excluded values. So I'm looking at the x values that make the original expression undefined. Now in these division problems, there are actually a few ways to make the expression undefined. We can have either of the original denominators have a value of 0, but we can also have the second numerator have a value of 0. If we have a value of 0 in that second numerator, then what we're really seeing is some expression, a over b, times 0 0 divided by c. So 0 divided by c is really just saying 0, and this was a division sign. So if we had a over b divided by 0, that would give us an undefined value. So in these division problems, there are actually 3 parts of the expression that we need to be careful about when we're thinking about excluded values. So another way to justify that is when I rewrite the problem as a multiplication problem, that second numerator that I was looking at becomes a denominator, and so it also can't have a value of 0 at any point in my calculation. So I've got x plus 4 over x plus 1. I want to make sure that 2x plus 1 does not have a value of 0, so that's going to give me an excluded value of negative 1/2. X plus 10 cannot have a value of 0, so that's going to give me an excluded value of negative 10. X minus 3 will give me an excluded value of 3. X plus 1 will give me a value of negative 1. X plus 4 will give me a value of negative 4. And 2x plus 1 I already saw. So that's a lot of excluded values, but that's okay. We're saying that our original expression is equivalent to x plus 4 over x plus 1, except when you plug in negative 1/2, negative 10, positive 3, negative 1, and negative 4. Let's look at a few examples, one multiplication and one division. So in this multiplication problem, we don't have factored numerators and denominators. So we're going to need to first do that so that when we multiply the numerators and denominators together, we'll be able to keep an eye out for those giant ones. So I'm going to do some of these fairly quickly, but remember that there are other videos out there about factoring quadratic expressions if you want some extra help with that. Looking at that first denominator, I notice a difference of squares. So x squared minus 1 can be factored using our difference of squares pattern into x plus 1 times x minus 1. If you don't believe me, multiply them back together with an area model and see if it works. That first numerator, I notice, has a common factor of 3. So I'm going to start by just factoring out the 3 so that my calculations get simpler later on. I notice similar things for the second numerator and denominator. The second numerator, that one actually doesn't have any common factors, so I'll hold off and use an area model on that. But my second denominator, I notice, has a common factor of 3. So I can write that as 3 times x squared plus 2x minus 8. Alright, and then I'll need an area model to find the factored version of 2x squared plus 13x plus 20. So I want to add to 13x and multiply to positive 40x squared. The factor pairs that multiply there are 1 times 40, 2 times 20, 3 doesn't go in, 4 times 10, 5 times 8, 6 doesn't go in, 7 doesn't go in, and we're back to 8. So looking at the things that add to positive 13x, I'm seeing 5x and 8x. Alright, I've got my area model filled in, and so now I'm going to get the outsides. I put a 2x there because I noticed that 2x multiplies into 2x squared and 8x, which gives me a base of x plus 4, And then x times 5 gives me an area of 5x, and 5 times 4 gives me an area of 20. So I can go back up here and write this as 2x plus 5 times x plus 4. Alright, and then I'll need area models to finish off the factoring, but I'm actually going to do that in my head. So I've got 3 times x minus 2 times x plus 1. I really encourage you to check these if you aren't sure how I'm getting those factored versions. And if you're getting something different, then please review that video about factoring quadratic expressions, or let me know that you think there's a typo. Alright, my second denominator there is going to be 3 times x plus 4 times x minus 2. Now I've got a multiplication problem, so I'm going to rewrite those as the numerators multiplied together and the denominators multiplied together. So I'll have 3 times x minus 2 times x plus 1 times 2x plus 5 times x plus 4. All divided by, I'm going to pull that coefficient of 3 out front because that's traditionally how we write these kinds of expressions. Makes it easier not to lose track of that information. Then I'm going to look for some giant ones. I see the 3 over 3 as a giant one. I see the x plus 1 over x plus 1 as a giant one. Got x minus 2 over x minus 2. X plus 4 over x plus 4. And so my final expression will be 2x plus 5 over x plus 1. I'm sorry, x minus 1. We want our excluded values to be the values of x that made the original expression undefined. So I'm seeing I don't want positive 1 or negative 1. I also don't want negative 4 or positive 2. So I'm looking at the factored version of the denominators from my original expression before I canceled anything out. If I wanted to check that this was correct, I would graph y equals 2x plus 5 over x minus 1 and y equals my original expression and make sure that those graphs look the same. Be careful though if you're doing that you don't miss any signs when you're typing it into Desmos, because it would really be a shame if you went back and combed over everything to find a mistake and the mistake had been in your typing into Desmos. So my last example here is a division problem. I'm going to need to start by factoring the numerators and denominators. And I'm going to do some of that with an area model and some of that in my head. But I am noticing here that my first denominator has a common factor of 2. So I'll pull that out first. Get 2 times x squared minus 2x minus 15. And in that denominator, I'm seeing a common factor of 6. So it'll be 6 times x squared minus 25. And divided by x plus 7 times x plus 3. And I see a common factor of 3 here, so I'll write that as 3 times x squared minus 3x minus 40. Alright, I almost have this fully factored. And here I'm going to finish factoring and rewrite it as a multiplication problem. So this numerator will be 2 times x minus 5 times x plus 3 over 6. Here's the difference of squares again, so I've got x minus 5 times x plus 5. Now I'm going to write it as times 3 times x. Here I want to multiply to negative 40 and add to negative 3. So let me draw out an area model for that one. I've got x squared minus 3x minus 40, and I'm adding to negative 3x and multiplying to negative 40 x squared. So I've got 1 times 40, 2 times 20, 3 doesn't go in, 4 times 10, 5 times 8. So I want to add to a negative, so I'll have negative 8x and positive 5x. So this, let me just make that a little bit clearer. Negative 8x. Okay, so I've got x by x to give me an area of x squared, and then positive 5, negative 8. So x minus 8 times x plus 5. And then my denominator, which is coming from x plus 7 times x plus 3, just gets rewritten there. Okay, so now I've got this written as a multiplication problem. And so I'm going to rewrite it. I'm going to pull the 2 and the 3. I'm going to combine. So 2 times 3 is 6. Times x minus 5 times x plus 3 times x minus 8 times x plus 5 divided by 6 times x minus 5 times x plus 5 times x plus 7 times x plus 3. Whew! So we're looking for giant ones here. The 6 over 6 I see as a giant one. X minus 5 over x minus 5. X plus 5 over x plus 5. X plus 3 over x plus 3. And so we are just left with x minus 8 over x plus 7. We want our excluded values here to be coming from a couple different places. Our original denominators and the expression that becomes our denominator when we rewrite it as multiplication. So let me just circle those in the fully factored version. I've got this here and both of these here. So I want excluded values of positive 5 and negative 5, of positive 8 and negative 5 we already saw, and negative 7 and negative 3. So that's that. We can check that by plugging in y equals the original expression and y equals the new expression into Desmos to make sure those graphs look the same. If you have any questions about anything that was in this video, be sure to check out the videos that have already been made, especially part 1 from this series and the factor and quadratic expressions video, or shoot me an email.